So here's our 12th and final video on the series. We're going to be looking at the family of antipedal triangles to a family of rotating equilaterals. Okay, so I want to look at the antipedal triangle. Let me move P away from the circumcircle so I can actually draw the antipedal. And I'll explain to you why this is in a second. So I'm rotating my equilaterals and I'm tracking the antipedals. Okay, now it turns out that if P is on the circumcircle, my antipedal is going to shrink to a point. Okay, so it shrinks to a point which is an antipode to P, right? So you can see here that my antipedal triangles now have zero area and they're all located over here. If I move P around, I get a different degenerate point triangle, okay, with zero area. Okay, what if P is inside? If P is inside, then my triangle has some shape. If P is outside, my triangle has some shape, and so forth and so on. Okay, so all right, this is a cool road to take. Let's see here. I'm going to refer to the script. All right, so first thing I'm going to do is the following. Let me actually go back to, so I'm going to place P on the inner circle. I'm going to place P on the inner circle. Now, first thing I want to show you guys, which is quite pleasing to the eye, is the locus of the vertices of my antecedent over the Poncelet family. There it is. So over, I'm calling it the Poncelet family. I don't need the term Poncelet here. This is just a family of rotating equilaterals. But over this family of rotating equilaterals, an incredible thing happens. The locus of the vertices of my antipedal triangles is a parabola, and the focus of this parabola is the antipode of P on the encircle. So here's the focus, is this green point, and I'm getting precisely now a parabola. If I move P around, I get a different parabola. All these parabolas are rigidly rotating, and their foci lie on the encircle. So I thought this was pretty cool. This must be classically known, okay, because it's such a sort of surface kind of observation. What happens if P is not on the encircle? So let's move that inside. So if I go inside, it's telling me now that I am in an ellipse kind of a configuration, and the nice thing is that one of the foci of this ellipse is still the antipode of P on this imaginary circle centered at the common center. So you could say that the focus is always the reflection of P about the common center. So I have this situation here where I'm an ellipse. I can be a parabola if P is on the encircle, and then when I'm outside the encircle, I'm a hyperbola. I'm a hyperbola. I'm not drawing the foci correctly. Still, there's a bug, but I can assure you that one of the foci is going to be as an antipode of P or a reflection of P about that point. I think if I move this R around, at some point I'm going to get to a correctly drawn hyperbola. Oh, maybe not. Okay, maybe not. Yeah, so when P is outside, I remain a hyperbola. You can see here that one of the foci of this hyperbola is, again, a reflection of P on the common center. If P is exactly on the outer circle, I cannot compute these loci, okay? Now, what happens to these loci? Let's go back to the parabola one, which was the sort of the simplest one. If I now apply an affine transformation to the system, let's go ahead and do that. What happens? I'm a non-conic, right? So the loci of my vertices now, you can see that there's a non-conic. They can even have some self-intersection, like this. If I jog now, this is now what we call the homothetic Poncelet family. It's a family of triangles which are affine images of the rotating equilaterals, but now I've lost that precious conic kind of property. So the conic seemingly will only happen when I go back to identity affine and back to the equilateral family, and I have this nice parabola. Okay, second property, looking at my script here, let's look at the locus of the barycenter of my antipedal triangles. That locus is a beautiful parabola, and its focus is P. I love this result, right? So I have two parabolas here. One of them is the locus of the vertices of my antipedals, and the second parabola is the locus of x2 of my antipedals. The focus of the former one is this reflection of P on the common center, and the focus of the locus of x2 is P itself. What if I move P slightly away from the incircle? I remain a conic, so the locus of x2 is saying here it's still a hyperbola, okay? And if I go inwards, I become an ellipse, and one of the foci of this ellipse is still point P. So I do believe in, if you ignore the bug on me drawing foci here of these hyperbola, right now I'm actually drawing the focus correctly. You can see here that one of the foci of the locus of x2, of the hyperbolic locus of x2, continues to be P. So it's P in the parabolic case and on the either elliptic or hyperbola case. One of the foci is always P. So that's quite nice, right, for our anti-Sevians, anti-antipedal triangles. Okay, how about if I now apply an affine? So let's go back to the default, which is the inner, where I got the hyperbola. If I apply an affine, now this is incredible. I actually did not make a note of this, but this is telling me that despite the affine, does that make sense? Everything is projectively invariant here, right? No, the pedal antipedal construction is not even affinely invariant. You need perpendiculars, right? So this is quite an incredible phenomenon here. We saw before that the locus of the vertices is something complicated, but what this is telling me is that the locus of my antipedal x2 remains a parabola if I'm on the Steiner inellipse of this family. That's quite incredible. So this locus is still a parabola. This is unique to this antipedal family. How about if P is not on this ellipse? Let's release P and let's bring P inwards. Okay, so now it's actually saying it's an ellipse. It's saying it's an ellipse. So it's a parabola if I'm on the Steiner inellipse. And then it goes to a hyperbola. I can compute it here. And then if I'm outside, looks like I'm getting a hyperbola as well. It's pretty stretched out hyperbola. So I think the salient phenomenon here is, of course, it's a conic throughout, but if P is on the Steinerian ellipse, quite incredibly, I'm remaining a parabola. And I'm showing the focus of the parabola here, which doesn't seem to be registered, at least right now, with any particular point. We could ask ourselves the question of what's the locus of this focus as P rotates about the Steiner in ellipse. Doesn't look like it's a very simple curve. It looks like it's actually going through itself. Yeah, it looks like it's a, it's a two-loop curve with a pinch point, kind of like a, what do you call those things? Figure 8 curve. Thinking about the name here, the lemniscate. I don't think it's going to be a perfect lemniscate of Bernoulli, but it looks like it has this sort of figure 8 shape, right? All right, so that's x2 with the affine when P is on the Steiner in ellipse. Let's go to our default home base here, which is, I'm going to go place, oops, what did I do here? Yeah, so this is some other phenomena that I don't want to discuss here. Yeah, so I want to go back to my family of equilaterals. I want to place P on the inner, on the incircle, and now I want to analyze the loci of x3. So here's x3. Very cool as well. It's telling me that over the family of equilaterals, the locus of x3 seems to be a parabola. Saying here numerically it's a parabola, and the focus of this parabola seems to be collinear with P and the common center. So if I move P around, still getting a parabola. That's quite nice. I'm sure the focus is now, the locus of this focus should be a circle. And as I rotate the family of equilaterals, x3 moves around on the parabola. Okay, what happens if P is not in that center, in that incircle, right? So if I go inside, I'm an ellipse. If I go outside of the incircle, I'm a hyperbola. And then if I go to the outside, I'm still a hyperbola. So yeah, it's maintaining its conic status throughout with this very cool situation here that if P is on the incircle, in the special case, X3 is a parabola. What if I apply an affine transformation? So let's go back to the inner. I'm going to start with this easy mode here. And I'm going to apply an affine. And what's happening? I'm a non-conic. So this guy is not surviving. Okay, so it's not surviving the affine. If P is moved around, it should be a non-conic throughout, unless there's some weird miracle. Let's put it exactly on the outer. Okay, there is a weird miracle. So when P is on the outer Steiner ellipse, the locus of X3 is an ellipse. Okay, but I do believe this is going to be the only case when this is happening. So X3 is moving along that very small ellipse, but it's numerically an ellipse. And if I deviate from the Steiner, I'm no longer an ellipse. So I only have one miracle here. If I'm on the Steiner, I'm an ellipse. If I'm on the inner, I am a non-conic with the affine applied. Okay? All right, so that's X3. Let's look at X4, X5, and X6 now very quickly. So go back to our home base. I want to be on the inner, and I want to look at X4, and I want to turn the triangle about. And this is quite an incredible phenomenon as well. I have it here on my script, perhaps the most interesting one. The fact that the locus of X4 of this family is a straight line. Okay? So you could ask yourself, what is the envelope over all P? And by symmetry, one would expect this envelope to be a circle, right? Okay, cool. What about if I now move P away from where it is? Let's move it inwards. It's an ellipse. Okay, if P is inside, very cool. What if P is outside of the incircle? It is a hyperbola. So we're undergoing this really interesting transition, right? If P is right on the incircle, you can see here that one of the branches of the hyperbola is going to become a straight line that is tangent to the circumcircle, and the other branch is just straightening out. So you're actually going to get a two parallel degenerate conic, and I cannot draw this bottom one here because X4 is just zipping through it very quickly. So you're going to see that X4 is just zipping through this very quickly, and the closer I am to the incircle, the faster will be this motion of X4 in this inner branch. So when I'm exactly on the inner branch is still there. There's a virtual tangent here that is parallel to this line, but you get a sort of couple of parallel lines that are a degenerate hyperbola or a degenerate ellipse that has gone to infinity, and I can say, okay, I only have one of the branches that lies in the real plane, the other one is in the line of infinity, and I'm basically getting to this situation here. Now, what if P is outside of the incircle? Let's keep moving it outside. I go back to hyperbola, and then when I reach this degenerate state here, I cannot compute it, but if I go outside, I'm a hyperbola. So the locus of X4 is a conic throughout, okay, with this really cool location here when, if it's on the incircle, I get a straight line. How about X? Okay, before we go to X5, let's see if this thing survives affine. So here's the affine. Okay, so X4 becomes a non-conic in the special situation. What if I go to the outer one? This doesn't make sense, right? It cannot be a conic. Okay, so if P is on the Steiner of now this affinely distorted family, the locus of X4 over the Poncelet family is now an ellipse. And am I seeing this right? It looks like this ellipse. No, the ellipse is not dynamically tangent, but it's always an ellipse. And it looks like wherever I place P, the axes of this ellipse, the minor or the minor and major axes of this elliptic locus are invariable with respect to P, which is a cool thing. That's cool. All right. What if P is not on the Steiner? What if P is outside the Steiner? It's a non-conic. It's a non-conic in the interior of the Steiner, and it's a non-conic even when P is on the incircle, on the image of the incircle under the affine, right? Okay, so I think the salient phenomenon regarding X4 is that it is an ellipse in general, and then as you reduce, as you bring x4 as you bring, is that what? Yeah. So as you bring P closer to the is that what we were seeing before? Yeah. So yeah. Okay. So yeah. So this is an interesting thing. So if P is on the in circle, as we saw before, x4 is a straight line provided there's no affine transformation. Okay. Now if there's a affine transformation, then the locus of x4 is an ellipse provided P is on the outer Steiner. Cool. Let's look at x5. So back to our home base. I'm going to go to the inner and I'm going to say x5. x5, oh, that's quite cool, right? So look at what's happening here. The locus of x5 over my family of equilaterals is a parabola if P is on the in circle, and the focus of this parabola looks like the center of the system. That's quite incredible. Okay, what happens if P is not on the in circle? Let's release it. Let's go inside. It's an ellipse, and one of the foci is a common center. If it's outside, it's going to be a hyperbola with one of the locus being the common center, and so forth and so on. So sometimes I have these deviations because there's infinity numbers that are pretty large because I'm not sort of culling them. I should cull numbers that fall too far away from the center here. And sometimes I'm doing numerics that are taking into account these sort of outlying numbers that shouldn't be going into the numerics, and I'm not correctly estimating the foci. But I can see the pattern here already. What's happening is if for any position of P, I'm always going to get a conic where one of the foci of this conic is a common center. Does this thing survive affine? Not if P is here. What if P is there? If P is here, it looks like it's x5 will be an ellipse if P is on the outer Steiner. Okay, but it's a pretty tiny ellipse. If P is on the inner Steiner, this is a non-conic, and so forth and so on. Okay, so good. So that's x5. Now let's go to the next one, x6. Let's see if there's anything of significance here. Let's go to the inner and throw in x6. Now x6 is quite cool, right? Because it is an ellipse over equilaterals. The ellipse is tangent to the circumcircle at a point that is probably collinear by symmetry here with the common center and P. So here's a point of tangency that is unmarked in the simulation. And one of its axes, the smaller one, so this is inherent to the equilateral family, is 0.4. So it's the circumradius times 0.4. What's 0.4 is like 2/5, right? So I have this 2/5 thing. We've seen before 1/5, 1/10. x6 is always calculating interesting ratios that have 5 in the denominator. So this guy is giving me an ellipse. If I move P around, I'm going to get a family of ellipses. What happens if P is detached from the inner circle? So let's go ahead and release that. Let's go inside. Let's go inside. Still an ellipse. That's nice. Still an ellipse if it's outside. And then I cannot calculate x6 when P is on the circumcircle. But if I'm outside, I'm still an ellipse. Let's increase the sampling ratio here, if I can. Yes. So x6 is an ellipse for all P over this family of, so x6 of the antipedal with respect to a point P anywhere over the family of equilaterals is always going to be an ellipse. Nice. Okay. Now, does this thing survive affine? It does not survive affine for P here. Does it survive affine for P on the outer? Yes, it's still an ellipse. So remember, I cannot compute x6 when P is on the outer because I cannot, for the equilateral case, because my antipedal triangles are zero area triangles and I can't properly compute where x6 is just going to coincide with the zero area triangle. It's not interesting. But if P is on the outer Steiner, the locus of x6 is an ellipse. It looks like it's an upright ellipse. Okay. If I keep moving inwards, if I keep moving P inwards, I'm no longer a conic. And then if I hit the inner guy, I don't get a conic. That's interesting. And if I keep going in, not a conic either. Okay, so x6 is only showing a few phenomena here. Let's move forward now. Let's go back to our home base, inner, and I'm just going to quickly zip through x7, non-conic. How about x8? non-conic, x9 non-conic, x10 non-conic, x11 non-conic, 12 non-conic, 13. And that's an interesting one. We're just going to go now through the final series of 13 through 16. x13 is the first Fermat point. It's telling me here that the locus of x13 is the antipode of P on the in circle when P is on the in circle. What happens if I let P move inwards? x13 is still a stationary point. That's nice. What if now P is outside of the in circle? Now x13 is going to be that bistable kind of locus where it has an isolated point and an arc of a circle. Isolated point for a while, arc of a circle for a while. We can analyze that, but let's keep going here just for brevity. Let's go ahead and now take P further out, and let's take P outside of the circumcircle, and we're going to get, again, a bistable phenomenon, but now you have this sort of longish arc here where x13 is on. Then you're going to go to the stable location there for a while. It stays there for a finite amount of time. Okay, that isolated point, and then it goes back to the arc. So it's a bistable. Okay, does x13 stationarity when P is inside of the incircle survive the affine transformation? Let's look at that. Doesn't look like it does. Okay, so it's a non-conic. And if I move P around, it's going to be doing some weird stuff. Too complicated to be analyzed. What if I'm exactly on? Okay, so here's one. There's always something hidden, right? If P is on the Steiner circumellipse, the locus of x13 of my antipedals with respect to P on the Steiner circumellipse exclusively is a circle. But anywhere else, you lose this sort of this harmony, right? So if I take P out, I'm this weird curve. If I take P in, I'm this other weird curve, and it doesn't matter where I am. If I'm on the inner, I'm not an ellipse. So the only phenomenon that is worth mentioning here is that the locus of x13 is a circle if P is on the Steiner. How about x14? Let's go back to our home base, x14, and if I'm on the inner. So that's nice. It looks like x14 is a circle if I'm on the inner ellipse. What if I go inside the inner ellipse? I remain a circle, and furthermore, I remain a circle of the same radius, which is quite nice. See that this circle is remaining, its radius remaining equal to 2. Now, what if I'm now outside of the in circle? Let's see if there's a transition. There's a transition to a bistable configuration. I have a long wait for x14 at this isolated point here, and then I suddenly jump to this arc of a circle here. It's actually telling me it's a parabola. That's interesting. I don't know if I trust that. The jury will be out here for a while, but this looks like, no, this cannot be a parabola, of course. So this is probably an arc of a circle, and I'm getting some numeric sampling error here. I'm probably sampling the wrong points, and it's thinking it's a parabola. I only sample 5 points to determine if something is a parabola. Should sample more. Okay, so that's x14 bistable. What happens if P is exterior to the circumcircle? Again, I have a bistable. Let's increase the sampling here so that we can see that this is properly a circular arc. Right here, this is a circular arc, and then I have this. I have a phase where x14 is just stuck at that isolated point, and another phase where it's actually quickly zipping through the circular arc. Okay, let's see if this thing survives affine transformations. Doesn't seem like it does. It's pretty complicated. But if I place P on the outer, okay, I got a similar phenomenon that I got before, which is the locus of x14, like x13, when P was on the outer ellipse, is a perfect circle. Probably nowhere else do we get that. How about x15? So x15 and x16 are related. They are sort of cousins of x13 and x14. Let's see what happens to x13, and I'm just going to stay right here, x15. So x15, also a very tiny circle with P on the Steiner. If I take P out of the Steiner, go in a bit, Complicated. If I go outside, complicated. How about if I go back to my equilaterals? X15 is a bistable arc of a circle and a stationary isolated point. When I'm outside, what if I'm inside? What if I'm on the circle? It's nothing because we're talking about antipedals here and they're degenerate. Let's go inside the circumcircle. So now I have a bistable again, arc of a circle plus a point. This is saying non-conic, so jury is still out, but these things tend to be arcs of circles. So let's keep going in to see if I go to the inner one. Okay, so I got a similar phenomenon that I got with X13. X15 is stable, is stationary. If I'm on the incircle, what if I'm inside the incircle? Also stationary. Great. So there's some cool phenomena here. If I apply the affine, I'm a circle. No, it's actually a non-conic. It's only a circle if I'm on the outer. Is that correct? Or on the inner? Exactly on it? No, so X15 is not giving me a circle either at the outer. It's giving me a point at the outer. That's quite nice. So this is the secret of X15. Is it? Oh, it's a circle. Yeah, it was looking like it was a point, but it's actually a circle. And we might have seen this just before. Yeah, so X15 is a circle if P is on the Steiner. X15 with the affine is a non-conic if P is on the inner conic. How about X16? Very quickly. X16 is a non-conic under the affine if P is on the Steiner and ellipse. If P is on the outer, X16 is a circle. Beautiful. Okay, so you're going to get similar things on the equilateral case. If I go over here and I go to the inner one, I'm going to get things that are complementary, right? So X16 is a circle over the equilaterals if P is on the incircle, and if P is on inside of that incircle, I continue to be a circle of constant radius equal to twice the circumradius. If I leave the incircle, now I'm piecewise bistable. I have an arc of a circle followed by an isolated point. Let's see this for a minute. I'm stable there at P, and then I sweep that arc of a circle and go back to the isolated point. Now, let me see if I can hazard this. If P now is moved to the outside of the incircle, of the circumcircle, I'm going to be a stationary point. Yeah, nope, I'm not, so I'm wrong. It's still bistable. It looks like I cannot be a stationary point with X16. It's either bistable. If I'm on the outer, it's stationary, but this is degenerate. Okay, so if I'm exactly on the circumcircle, this is degenerate because my antipedals are just this point, and then X16 is that point, and that's going to happen to a whole lot of triangle centers which are going to be computed by just triangle that has no area. If I'm on the inner, I'm getting a circle over here, and if I am medial link, I'm getting nothing. Variable, go out, yeah, over here. Okay. I think that this is a good place to stop. We've had a series of 12 videos. I thought this was just a bunch of trifle comments about triangles rotating, equilaterals rotating about a circle, rotating about their centroid. I started with the anti-Sevian all the way back in video 1. I showed this result to a couple of colleagues, especially Professor Ronaldo, who said, hey, you should try anti-Sevians, you should try pedals, antipedals, you should vary the R, the distance of P from the center of the system. And as I added these additional dimensions, I started to discover a whole lot of phenomena. I'm sure that they are measurable in dozens of them, right? I think over these 12 videos, we easily went through 20 or 30 or 40 phenomena. So I hope you guys enjoyed it, and I'll see you in the next video. Bye.